Let's take a look at the classic 6 simple machines. Let's start by considering what is a machine. A machine is anything that converts energy into some form of useful work. If a machine is 100% efficient, then all of the input energy would be converted to useful work, but this is just not possible, and some of the energy is always wasted. This is where the second law of thermodynamics comes into play, but you don't have to worry about that for now. So, what then is work? Well, if we consider a force, F, acting on an object to move it along some linear path by a distance x, and if F is acting in the direction of the motion, then the work being done on the object is the integral of the force over the distance. If the force is not acting exclusively in the direction of the motion, for example, here it is acting downward and to the right, then we can decompose it into a component acting in the direction of motion, which contributes to the work done, and a component acting perpendicular to the motion, which does no work. For the case of rotational motion, we consider torque and the angular displacement. For example, if you tighten a bolt by applying a torque T to a wrench, and you turn the bolt by some angle theta, then the work you have done is the integral of T d theta. Okay, so the first simple machine to consider is the lever. Here we have a weight W located at a distance A from the fulcrum, and we'll apply a force F at a distance of B from the fulcrum. If this system was 100% efficient, which we know it's not, but let's pretend anyway, then the downward force required to raise the weight will be W multiplied by the ratio of A over B. So a lever makes it easier for us to move heavy objects, and by easier, I mean with lower forces. However, to raise the weight some distance dW requires us to apply the force F over a larger distance. The energy input then would be F times dF, which is equal to W times A over B, times dW times B over A, which is just equal to W times dW, which is the useful work out. Of course, in reality, some of the input energy is lost to friction and deformation of the lever, so this relation is not quite correct, but you get the picture. And speaking of pictures, here are some levers. Our second simple machine is the pulley. Pulleys are used to change the direction of a force, and like the lever, they can be used to amplify a force at a cost of increased travel distance. Here we have a cord wrapped around 2 pulleys with the weight W attached to one of the pulleys. Incidentally, this set of short diagonal lines is the way we indicate a surface that is stationary. Now, if we want to raise the weight, we have to pull on the cord with some force F. Assuming a perfectly efficient system, then the force required is half the weight. This is because the other half of the weight is being supported by the ceiling. And if we want to raise the weight by some distance dW, then we have to exert the force F over twice that distance. And here are some examples of pulleys. The third simple machine is the wheel and axle. In this example, the wheel and axle is used to raise a heavy weight by pulling with a smaller force on a cord. As with the lever and the pulley, the distance over which the force acts, i.e. the amount of cord that must be pulled, is greater than the distance the weight will be raised. The wheel and axle can be used to convert linear motion, such as pulling on a cord or pushing on the rim of a wheelchair, into rotational motion, or to convert torque into a rolling motion along a surface, or to transmit torque from one axle to another, as in these gears. The fourth simple machine is the inclined plane. Suppose we want to raise a weight W up to some height h. The force required to lift it straight up would be simply W, and the work we would have to exert would be W times h. Suppose we instead pushed it up an inclined plane at some angle theta with the ground. If we draw a free body diagram of the weight on the plane and identify the forces acting on it, we have the weight W acting downward, the force F acting in the direction of the plane, and the force from the plane pushing against the weight. We call this a normal force. The word normal in this context means perpendicular. We can decompose the weight force into one component acting in the direction of the plane and another component normal to the plane. Then, if we assume the surface is frictionless, the force F required to push the weight along the incline is W times the sine of theta. Actually, this is the force required to keep the weight from sliding down the plane. The force to move it up the plane has to be just slightly larger than this. Now the work required to push the weight up the incline to a height h is F times this distance, which is the same amount of work required to lift the weight straight up to the height h. However, the pushing force is significantly less, and the distance of travel is significantly more. Here are some inclined planes. The fifth simple machine is the wedge. The wedge is used to convert force and or motion in one direction to force and or motion in a perpendicular direction. Here, as the wedge is forced downward into the block, it exerts force to the left and to the right, causing the block to split and move outward. Here are some examples of wedges. Finally, the sixth simple machine is the screw. A screw is essentially an inclined plane helically wrapped around an axis. Screws are used as fasteners to join objects together, but a screw is also a machine, which converts rotational motion into linear motion. So those are the classic 6 simple machines. Many devices, of course, combine these simple machines into what we call compound machines, such as this can opener, shovel, and corkscrew.